Hey guys, welcome back to another interesting topic. Today's topic is about binary multiplier. So before going to binary multiplier, if you are new to my channel, please do subscribe and hit that notification bell so that we can get connected. And if you have any doubts, comment down below. I will respond within 24 hours. So without any further delay, let's go to binary multiplier. So we need to add binary numbers, we use full adders. So to multiply a binary numbers, we need to use a binary multiplier. So binary multiplier is a combinational circuit that performs multiplication on two binary numbers. So to understand this carefully and analyze it, let's take an example of 2 bits and then we will increase the number of bits for our better understanding. So now let's go with 2 bits multiplied with 2 bits. So as you can see over here, I have taken a bit A, binary bit A and binary bit A, B, which consists of A1 and A0 as a 2 bits binary number. So and B1 and B0. So here A is called as multiplicand and B is called as multiplier. So now let us multiply them. It is normal multiplication how you do in a decimal form, same multiplication, but these are binary numbers. So now let's multiply them. So B0 is multiplied with A0 and A1. So it is B0, A0 and B0, A1. So now that's B0 done. Now we need to multiply with B1. So and add them. So first we need to shift by 1 bit, that is B1 and A0 and B1 and A1. So these are the partial products. So these are called as a partial products. So now we need to add them up to get our final result, that is the binary multiplication of a 2-bit. So I have written Z0, Z1 and Z2. You can call it as Z, no problem, but I'm not writing the total term over here because it will be nasty. Okay, here Z1 is B0A1 plus B1A0 and Z2 is if any carry comes from this term here, which will be added over here, B1 and A1, and there will be a carry from here also, so I'm writing a C as a carry for it. Okay, so this is the basic binary multiplication, and now let's design the circuit, how to implement this circuit using the half adders and AND gates. So as you can see, we need AND gates. How many AND gates do we need? We need A0 B0, A1 B0, A0 B1 and A1 B1. So we require 4 AND gates for this products, partial products. After partial products are done, we need to add them up. So we need adders. So what kind of adders do we need? We need half adders because we have only 2 terms over here and a carry over here, and it will be added with A1 and B1 if carry is there. So we need 2 half adders. So now let us go into the circuit. So first we will draw AND gates for partial products. So as you can see, these are our partial products: A0, B0, A1, B0, A0, B1 and A1 and B1. So after getting the partial products, we need to add 2 terms. We need to add these 2 terms, which will be a half adder required for it, and if there is a carry, so for our safety there will be a half adder required for it. So we require 2 half adders. Let's see how it will be. So the first term doesn't require any half adders, but the second term requires the half adders, which we need to add these 2 terms. Okay, and this carry will be used for the next term. So we are taking this carry and giving it to the half adder. Okay, and there will be a carry if we add this 2, so that's our C. So this is how we design a 2-bit binary multiplier. Okay, 2-bit into 2-bit. This is how it's done. So now I can use half adders or I can use a parallel adder. So now let's implement this binary multiplier in a parallel adder. So I'm using the same bits again, A and B, where it has 2 bits, A1 and A0, B1 and B0. A is the multiplicand, B is the multiplier, and again we are multiplying in a similar fashion. So that is B0, A0, B0, A1 and B1, A0 and B1, A1. Now we will add them again. It is similar to the previous case and it is the same example too. So I'm considering B0, A0 as Z1, Z0 and B0, A1 plus B1, A0 as Z1, and if there is any carry plus B1, A1, I'm considering as Z2. So I'm also taking a carry if there is a carry from here. So these are the outputs from our inputs when multiplied. So what's a parallel adder? Parallel adder is just like, so parallel adders looks like this. So this is a 2-bit parallel adder. Okay, this is a 2-bit adder where we will use 2 bits over here and add it. We'll get the carry in from here, and carry in will be propagated to this full adder, and we'll get the carry in and the output. So now we are going to use a parallel adder in our design, not the half adders. We are going to use this one. Okay, so as you can see over here we have partial products. Okay, these are the partial products, and as you can look them clearly, if we add a 0 over here, suppose I'm saying that there's a carry 0, okay, and if we add a 0 over here, there is no problem, it is a 0 over here. So if I consider this whole as one term x, and if I consider this whole term as y, that means x has x0, x1 and x2, and y has y0, y1 and y2. So this is looking like what? This is looking like an addition of 2 bits, okay. This x and y are being added. So now I'm going to use a parallel adder to show you how it's done. Let's go for parallel adder. Since we need to add these two terms, b0, a1, b1 and a0, so I'm considering this 2 and this 2. We need to add this 2 and this 2. Let's go to the parallel adder. So as you can see over here, I have used that same terms b0, a1 and b1, a0. These are z1 terms, z1 output terms. So we need to add them, and this carry will be propagated to this full adder and will be added with b1 and a1 if there is a carry. Okay, so what will be Cin? Cin will be 0. So Cin will be 0 because there is no carry. Okay, there is no carry from this. There will be no carry from here, so Cin will be 0. So this is the parallel adder, 2-bit parallel adder, which will be required for a binary multiplier with 2-bit into 2-bit. So now let us design it using our AND gates and show you in a complete picture. So as you can see, we require AND gates for our partial products, that is A0, B0, A1, B0 and B1, A0 and B1, A1. So these are the partial products. As you can see, we need a 2-bit adder, and we got our terms, argand terms and addend terms. I don't know how to pronounce it. If it might be wrong, no problem. Okay, we need to add the 0 over here. You know, I've shown you where the 0 is there. So whatever I've shown you, the previous circuit will be inside this. Wait a second, I'll show you once again. So this circuit will be inside that adder, 2-bit adder, and we'll get the output Z1 and Z2. So Z1 and Z2 will be the sums, okay. Z1 and Z2 will be the S0 and S1 respectively, and we will get a carry. This is a carry. So this is what the total circuit is. Okay, I hope you understood. So before going, I'm going to discuss a very important point right now. Be patient right now and listen it carefully, because this is most important rather than the whole thing, because you can decide, you can design adders whatever you want, and to decide it faster, let's go it now. So this is very important. Okay, I'm gonna say how many number of AND gates are required just by looking at the number of bits of A and B only, and how much will be the number of bits in the output product will be set by A and B. So now let us go and look into detailed terms. Okay, don't forget it. So now let's say A has m bits, that is its multiplicand, and B is n bits, and it's a multiplier. So number of AND gates, that means the partial products, number of partial products will be there in our multiplication is n into n cross m. So we have seen, and our example is 2-bit into 2-bit. How many AND gates are there? So how many AND gates are there in 2-bit cross 2-bit? So it's 2 cross 2, that is 4. So we require 4. So we require 4 AND gates. See, I haven't looked at the circuit. Okay, we know the circuit is like this. We require 4 AND gates. I haven't looked at the circuit. Then also we can say just by looking at the number of bits. Okay. Now what will be the total number of bits in the output product? What will be the total number of bits? So it is n plus m. That is 2 plus 2. We will have 4 bits as output for 2-bit cross 2-bit. So what are the number of outputs we got? That is Z0, Z1, Z2 and C. So how many bits? That's 4 bits. Okay, that's also correct. So now let us look at how many adders, parallel adders do we need. So we need n minus 1 number. This is the number. And what is that bit of adders? 2-bit or 3-bit, that is m bit adders. So what is n in 2 by 2? So we require 1 2-bit adders. Okay, 2-bit adder. Okay, no problem. We require 1 2-bit adder. I hope if it is another bit, let's say it is 3-bit cross 2-bit, then it will be 3 over here. 3 into 2 it will be 6. So 3 into 2 it will be 6. So we require 6 AND gates for 3 cross 2, and we require 5 output bits for 3 cross 2. And how many adders? So we require 3-bit parallel adders for 1 3-bit parallel adder for 3 cross 2. I'm not saying how many half adders are required. I'm saying how many parallel adders are required. Okay, so this is the parallel adder, and how much bit, what is the size of the, it is a 2-bit adder in our previous case, and in this case we require 3-bit adder. I hope you understood about binary adders. If you have understood a bit, thanks for watching till the end, and hope you subscribe. And if you have any doubts, please do comment down below. I will respond within 24 hours and clarify your doubts, most probably. Okay, and thanks for watching. And please do hit that like button and please do subscribe. Thank you for watching from heart.